Good morning, everyone. Welcome back, and thanks for joining our fully virtual session on coastal acidification. In this session, you're going to hear an overview of coastal acidification and the EPA National Estuary Program's Coastal Acidification Monitoring Program. That's going to be followed by presentations on acidification research and monitoring activities in Tampa Bay and the Indian River Lagoon. And then we'll hear about the effects of acidification on the Florida stone crab. For those of you online, please enter your questions in the chat. For our speakers, Ed will be advancing the slides for everyone, so please remember to say next slide when you're ready. And we ask that everyone please keep your videos off to reduce the risk of technical problems. I'd like to begin by thanking Dr. Rosenau, Dr. Nick Rosenau, my co-leader for this session. Nick is from the EPA's Oceans and Coastal Management Branch, Office of Wetlands, Oceans, and Watersheds, and he will be starting our session with a presentation titled Coastal Acidification Monitoring in the U.S. EPA National Estuary. Nick, take it away.
Thank you very much, Kim. Can I get a sound check as well? Can you hear me okay?
I can hear you. Ed, please also sound check.
We can hear.
Okay, perfect. Thank you so much. Thank you very much for the introduction, Kim, and thanks to our presenters and those of you attending the session today. As Kim mentioned, my name is Nick Rosenau from EPA's Office of Water. My co-author Holly Galavotti and I are both in the Ocean and Coastal Management Branch. And I'd like to kick off the session today with an overview of coastal acidification monitoring and EPA's National Estuary Program. Next slide, please. Okay, so we'll start off by what is ocean acidification? I assume that everybody is very familiar with this. It's a very hot topic, but just to kind of do a very high level overview of it, essentially when carbon dioxide is absorbed in seawater, chemical reactions occur, and that reduces the seawater pH, carbonate ion concentrations, and saturation state of very important calcium carbonate minerals. And together, these decreases or these reactions are termed ocean acidification. It's typically caused by, or it is caused by, increases in CO2 emissions absorbed by the ocean. And you can see that in a nice visual representation over here from a very popular, or very common curve. If you want to take a look at the curve here of CO2 as measured in Mauna Loa, and also plotted on there in green and blue respectively are seawater CO2 and seawater pH units. So what you can see is the steady increase in atmospheric CO2, and along the same lines, you see this increase in seawater CO2 and a fall in pH. And so we've seen this decrease in since about 1850 of about 0.1 pH units, from about 8.2 to 8.1, and it's happening at a much faster rate than any time measured. So it's a very big concern. And then estimates of future CO2 levels, if we do business as usual, indicate that by the end of this century, we're looking at surface waters where we could have acidity levels nearly 150% higher, and resulting in pH in oceans that we haven't seen in tens of millions of years. So it's a very big concern. Next slide, please. So briefly on the chemistry of ocean acidification, this is highly simplified, but essentially when atmospheric CO2 is dissolved in water, it forms a weak carbonic acid, which then easily dissociates into bicarbonate ions and hydrogen ions. The increase in these hydrogen ions are what make the water acidic. It lowers the pH. Like calcium ions, which there's a competition here, right? So hydrogen ions tend to bond with carbonates. So there's lots of calcium secreting and organisms in the water that need this, that need to actually use this carbonate, but it's unavailable a lot of times because of this increase in hydrogen concentrations in the water. And so studies have shown that a decrease in these carbonate saturation states, which is associated with these increasing hydrogen ion concentrations, can have a dramatic effect on a lot of calcifying species, including oysters, clams, urchins, corals, etc. And this is really a big problem because many billions of people worldwide rely on these food from these organisms as their primary sources of protein. So it's a very important issue. And as mentioned here on the slide, about 30% of all fossil fuel emissions has been absorbed by the oceans itself. So It's a big sink, but it can't hold it all forever. And there are lots of associated changes that go along with the chemistry of the ocean and the biology in the ocean. Next slide, please. So what is coastal acidification? Well, it's sort of ocean acidification plus, is the way I like to think about it. So there's ocean acidification that's occurring just from CO2 exchanging with in the atmosphere into the ocean, but also there's lots of other natural and anthropogenic drivers that make carbonate chemistry in these estuarine or coastal settings highly variable. So we're not looking only at CO2 from the atmosphere, we're looking at also land-based inputs that can both contribute and buffer acidification in some instances. Of these, some of the major ones you may have heard of are nutrient runoff from stormwater, agricultural activities, wastewater treatment plants. All these can promote algal growth, and eventually this can lead to hypoxia as you have organic matter that breaks down, and this can increase CO2, decrease oxygen, and not a good place for organisms to live in the water. We can also have lots of we have freshwater runoff that can contribute as well. In some cases, that can actually buffer acidification. So it's a much more complex system, as can be seen here on this nice diagram from a 2020 annual review paper by Kai et al. So understanding these local drivers and their variability is very important to understand how vulnerable these systems are, and determining what appropriate management strategies might be employed. Next slide, please. So now on to a little bit about US EPA's National Estuary Program, or the NEP. It's a place-based program that was enacted or put into place in '87 with the goal of protecting and restoring water quality and ecological integrity of estuaries of national significance. So currently there are 28 of them located along the Atlantic, Gulf, and Pacific coasts and in Puerto Rico. Each NEP focuses within a study area, and that includes the estuary as well as the surrounding watershed. Importantly, the priorities are defined by local, city, state, federal, and private and nonprofit stakeholders. They vary from NEP to NEP. EPA headquarters in the regions provide funding and oversight and manage the program, as well as guidance and technical assistance. But the local NEPs and the people, the boots on the ground at the institutions and at the local and state level and at the universities do all of the real hard work. That's the way I like to think about it. So there's 28 of them currently. And if we go on to the next slide here, please, Ed, we'll talk a little bit about those that have been conducting acidification monitoring. So back in 2015-16, I guess that's been 5 or 6 years now, EPA funded sensors to collect CO2 and PCO2 and pH data in 9 of these programs. It's kind of hard to see on this map here. Some of them are up in, there's several of them up in the Northeast, Tampa Bay, and Mission Aransas down in the Gulf, and then a few on the West Coast as well. Since that time, several more of these programs have begun monitoring, including Mobile Bay, and you'll hear about Indian River Lagoon a little bit today as well. But these NEPs face different stressors, different coastal water dynamics, and they all have different economic interests as well. So you'll see that there's overarching goals of the coastal acidification monitoring program, but much of it is dictated at the local level about what specific questions or concerns they have, depending upon what NEP or what part of the country you're in or what coast. Next slide, please. So I won't read all these goals to you, but these are just a smattering of the different goals that have been provided. When you ask the NEPs that are conducting this acidification monitoring, what are your goals? What do you want to get out of collecting this data? Why do you think you need to collect high or continuous CO2 and pH data and temperature and salinity data? What's that going to tell you? I think some of the big ones here is to really start to establish this carbonate chemistry baseline data in their estuaries and to begin to characterize variability at high temporal resolution. Of course, there's an interest in understanding these land-based versus oceanic influences on carbonate chemistry. And then in some cases, of course, the impacts of shellfish is critically important, especially up in the Northeast. I mean, that is critical to their economy, especially. So understanding these impacts are critical. Next slide, please. So a summary of this was put out by the NEP partners and EPA back in May of 2001. It talks about measuring coastal acidification in the National Estuary Program using these high-resolution in situ sensors. It's a really nice report. I would suggest go take a look at it. It's publicly available on EPA's website. And it goes through the different monitoring goals that I just mentioned, the different sensors that were used, deployment methods, some of the challenges and lessons learned, which is a really, I think, particularly interesting part of the report, and some preliminary results. It was nice. It does a nice job of providing this information sharing and technology transfer among the National Estuary programs for others to really learn from each other. And hopefully provides a little bit more face time to the issue of acidification in these coastal systems to start to drive some management plans and adaptation strategies moving forward. Next slide, please. And so the second part of this I want to mention is one other report that came out of this work. So this is a paper that came out late last year. It was a paper that was written with various people from 7 different NEPs, and the goal was to really look at data from across these 7 national estuary programs. So we don't have 9 here. We've got data from 7 NEPs, and looking at data for PCO2, pH, salinity, temperature, DO in terms of like their typical values. What is their median range of the data, seasonality, covariability of parameters, that sort of thing, to really begin to understand the natural variability across a range of environmental settings. And so we started to do that and take a look at that at a very high level. And you'll see that there's 3 West Coast NEPs that are part of this work, 2 from the Gulf, Tampa Bay and Mission Aransas, and then a couple from the northeastern part of the United States. So on these next couple slides, next slide, please, I will show you some of the data from this just really quickly. So what you're looking at here is, so you're looking at PCO2 data collected using these in-situ sensors from 7 different national estuary programs. And you're seeing it plotted on box and whisker plots, and it's plotted from lowest median PCO2 to highest median PCO2. So Mission Aransas Estuary in the Gulf is shown over there on the far left kind of box. And on the far right, you'll see Barnegat Bay with a very qualitative red line pushed through there just to kind of show this. And there's a lot going on here, but I think what we were trying to get you to take home here is just the intense or the great amount of variability both within a single estuary. Look at Tillamook, for example. I mean, you're getting values of CO2 from less than 200 to up to 1,400 parts per million, compared to what we might see globally in the open ocean. These are very different, very dynamic systems that have a lot of internal variability, and the variability among these systems is also quite large. Next slide, please. Next slide is the same sort of way that the data is organized in the same way, except here you're looking at pH data. So pH data sort of stores that inverse relationship where you're seeing some of the highest pH values, where you saw some of the lowest PCO2 values, for example, in Mission Aransas in the Gulf. And then you're seeing, again, a lot of that variability in pH data, which is driven by a lot of different drivers that we did not get into in this paper here. So I'm getting low on time here. Next slide, please. I just lastly want to show one other way of looking at this, which is a nice way of doing this, looking at data stacks, where you can plot different parameters together to get a better sense of what's going on. Here's an example of PCO2, DO, salinity, and temperature from Santa Monica Bay. And what we're seeing here is a clear, what we think to be a coastal upwelling signal, where you've got high PCO2, you've got cold water, and it's very saline. And that jives with what we know about coastal upwelling in this system. Last slide, please. Next slide, please. So I'll just leave it and say that these centers are doing a really nice job, we think, of capturing relationships, and that high resolution monitoring will be critical for understanding how these coastal systems are changing in the future. And I do want to get the last slide, please, moving forward, and then I will be quiet. So there's lots of questions moving forward. You'll hear about some of these today. They're already starting to be addressed. How much data? How do we address the difficulties associated with detecting trends? What other data do we need? And how can we use these to inform mitigation adaptive management strategies? There's a couple of new EPA reports coming out. Be on the lookout for those, please. And I will say that as my last slide and move to the next slide and just say thank you very much and acknowledgements there. If you have any questions, I'm happy to receive them via email as well. Thank you.
Thank you, Nick. Do we have time for a question? Ed in the room?
Yes, Kim, we're here. I'm just about to queue up your slide, and give me just a sec.
Okay. All
Do you
right,
have any-
so if we, I'm having a little bit of trouble hearing you, so is that no questions?
No questions, Kim.
Okay, thank you very much. So I will be giving the next presentation and introducing myself. Again, I'm Kim Yates. I'm a research oceanographer with the U.S. Geological Survey in the St. Petersburg Coastal and Marine Science Center. And today I'll be talking to you in a little bit more detail about our coastal acidification work in Tampa Bay, which is part of the NEP's Coastal Acidification Monitoring Program, as Nick just discussed. And I want to begin by thanking my co-authors listed here. We partner with the Tampa Bay Estuary Program and more than 20 collaborators across these 8 agencies and institutions who make this work possible. We have several local drivers of coastal acidification in Tampa Bay, and I wanted to begin by showing you this map of land use in the Tampa Bay watershed. This shows urban areas in red, mining areas in purple, and agricultural areas in yellow. It's bright, the colors are bright, so it might help wake folks up as their morning coffee wears off. But it's also a good reminder to us that we have a lot of land use issues that affect all of the coastal research and management that we've been hearing about for the past few days, including acidification. We have 4 rivers delivering low pH, high CO2 water and nutrients from this 2,200 square mile watershed. We experience algae blooms that can increase pH, but also cause post-bloom acidification events. Much of Florida, including Tampa Bay, sits on carbonate bedrock and sediments that can dissolve during low pH conditions. And despite the extensive urbanization throughout the watershed, Tampa Bay has more than 40,000 acres of seagrass around its perimeter, which you can see in green on the map. And this affects pH and CO2 through photosynthesis and respiration. Next slide, please. As many of you in the room know, Tampa Bay is actually a success story with respect to water quality and seagrass restoration. Nitrogen loads to Tampa Bay, shown in the top graph, were at their highest levels back in the 1970s and early 80s, which caused frequent algae blooms and loss of seagrass throughout the bay. And these loads have decreased over time through implementation of a successful decades-long nitrogen management strategy by the local community in the Tampa Bay Estuary Program, and including many folks who are participating in this meeting. And as a result, we've been able to restore seagrass back to 1950s levels. The dots on the bottom graph show mean monthly pH in the bay, and the green bars show seagrass acreage over the same time period. And when nitrogen loads were high, algae blooms caused extreme highs and lows in pH and after blooms, and you can see this on the left side of the graph. And then with the nitrogen management strategy, pH began to stabilize as nitrogen loads and algae blooms decreased, and you can see that pH has actually increased over the years as seagrass has been restored. So one of our primary objectives for this work is to examine the role of the nitrogen management strategy in seagrass restoration in buffering acidification as a restoration benefit. But these historical data are only daytime measurements, and we really needed higher resolution diurnal pH and CO2 data to better examine acidification chemistry and the processes controlling it. Next slide, please. So we began this work in 2015. We conducted a pilot study to inform development of our acidification monitoring approach. We established transects inside and outside of seagrass beds in what we considered end-member bay environments in upper and lower Tampa Bay, ranging from low to high % carbonate sediments and water mass residence times. And we measured spatial and temporal variability of the carbonate system along these transects to examine the biological and physical controls on the water chemistry. And some of our key findings were that seagrass can locally increase or decrease pH up to about half a pH unit, which is actually quite a lot, and PCO2 by more than 500 microatmospheres. We have very high spatial and temporal diurnal variability. We have very strong tide and water mass residence time control, with longer water mass residence times amplifying these chemical signatures. And we also saw evidence for calcification and carbonate dissolution in these seagrass beds. Next slide, please. This is an example of some of our pilot study results for pH, CO2, and total alkalinity, with Upper Tampa Bay on the left row of graphs and Lower Tampa Bay on the right. Each of these lines shows concurrent measurements along a transect from dense seagrass to bare sand. You can see the little cartoon at the bottom, at a specific time of day, with blue colors indicating night measurements and red colors indicating day measurements. And you can see the effect of seagrass photosynthesis and respiration on pH and CO2 during the day and night in that top set of 4 graphs. We're particularly interested in carbonate dissolution because it sequesters CO2 as bicarbonate and buffers acidification. It also has some blue carbon implications. This can happen in seagrass beds through a process that we call the bicarbonate pathway. And seagrass rhizomes can release oxygen into the sediments, which oxidizes organic material and produces CO2. That CO2 dissolves carbonate into calcium and bicarbonate ions, which increases alkalinity and buffers pH. And so we can use total alkalinity as a proxy for calcification and dissolution. And in the bottom right graph, you can see in lower Tampa Bay, where we have a higher percentage of carbonate sediments, we have a strong dissolution signature with the higher total alkalinity during the nighttime measurements, particularly in seagrass. And we typically see this when pH is less than approximately 7.9 and CO2 is greater than about 600 microatmospheres. So our question became, is there a bay-wide benefit from photosynthesis and dissolution, and where should we monitor? Next slide, please. We deployed a sensor package in lower middle Tampa Bay on one of the USF port stations in December of 2017. This location is a narrower part of the bay. It's relatively shallow and well mixed. It's tidally influenced, and it's located on bare sand bottom more than 2 kilometers away from the nearest seagrass beds. And our goal here was to capture a mixed bay water chemistry signature on outgoing tides with it purposely far away from seagrass so we can see if we're picking up any kind of signature that far away, and to track the Gulf of Mexico signatures on incoming tides. And we placed a second package 55 miles offshore in the Gulf of Mexico on one of the USF comps buoys in October of 2018 as an offshore reference site. We collect hourly pH, salinity, temperature, dissolved oxygen, CO2, and light measurements from these sensors. And we visit these sensors approximately monthly to quarterly to collect discrete measurements of total alkalinity, total carbon, and pH for validation of our sensor data. Next slide, please. These are the results from our first 2.5 years of sensor data with Tampa Bay data in black and Gulf of Mexico data in red. We can see that we have much greater diurnal and short-term variability in the bay as opposed to the Gulf of Mexico, which we might expect. There are distinct differences between Bay and Gulf of Mexico salinity and CO2 values, which provide good end members to help us distinguish between Bay and Gulf of Mexico chemical signatures. And the dotted lines on the pH and CO2 graphs show approximately 30% of our data falls below that pH threshold of 7.9 and above a PCO2 of 600, which is typically when we see that evidence of carbonate dissolution. And exposure to these more acidic conditions occurs primarily during the wet season, and this is likely due to river water influence. If you look at the red text on the right side of this slide, you can see the very low range of river pH flowing into the bay, as low as 6.7, relative to mean Bay and Gulf of Mexico pH of about 7.9 and 8.1, respectively. Next slide, please. Our Tampa Bay sensor sits between the inflow from 2 of the 4 rivers in Tampa Bay. It's a little bit closer to the Little Manatee River than the Manatee River. This top graph shows sensor salinity data in gray, plotted along with daily mean river discharge from both rivers in black and precipitation in blue. We have distinct dry seasons from mid-May to October and wet seasons from about November to mid-May, and this is reflected in our salinity data. The bottom graph shows a good linear relationship between daily mean salinity from our sensors and cumulative river discharge, and this indicates that salinity at our monitoring site is strongly influenced by these 2 rivers. Next slide, please. We performed correlation analyses on our dry season and wet season data to help identify controls on the water chemistry. And these graphs show correlation of pH, CO2, and dissolved oxygen with temperature in the pink columns, salinity in the middle blue columns, and among each other in the green columns. During the dry season, we see strong correlation of all 3 of these variables with temperature. We see very weak correlation with salinity and strong correlation among pH, CO2, and dissolved oxygen, hinting at some biological control, but all 3 of these variables are also very temperature dependent. During the wet season, we see only weak to moderate correlation of all 3 variables with temperature, very weak correlation with salinity, and strong correlation among pH, CO2, and dissolved oxygen, in fact indicating that we do see strong biological control from photosynthesis and respiration at this site. Next slide, please. As a very simple first approach to try to further tease out the biological signature and potential for bay-wide effects, we also filtered these data by high and low tide, day and night, high tide day and night, low tide day and night, daytime high and low tide, and nighttime high and low tide. And I'll give you a second to look at that graph so you can see the columns that show that. And then we tested for significant differences between means for these paired environmental conditions for dissolved oxygen on the top, CO2 in the middle, and pH on the bottom. Means for these variables were significantly different for all of these paired conditions except for those highlighted in pink. The green highlight shows when we have higher mean pH in dissolved oxygen and lower mean CO2 during either low tide or daytime. And in fact, we see the highest pH in dissolved oxygen and lowest CO2 during daytime at low tide, suggesting that we do in fact see some benefit from bay photosynthesis at this location. Next slide, please. We also examined our discrete validation data to identify potential Gulf of Mexico and river influences at this site on the carbonate system. These graphs show our discrete total alkalinity and total carbon data for Tampa Bay during the dry season in black and wet season in red circles. The graph on the right is zoomed in on that small box in the bottom graph. The red and black lines show end-member mixing zones between mean Gulf of Mexico and river total alkalinity and total carbon for the wet season and dry season, respectively. And data would typically fall along or between these lines if it were affected primarily by mixing of Gulf of Mexico and river water. But in fact, we see that much of our data falls well outside of this mixing zone, indicating that these variables are also influenced by other processes. And Chris Moore in the next presentation is going to discuss these river influences on the bay chemistry in a bit more detail in the next presentation. Next slide, please. If you pay attention to the graph on the left, salinity normalized total alkalinity and total carbon actually covary predictably in response to photosynthesis, respiration, calcification, and dissolution. And these relationships are shown in that graph on the left. Data only affected by photosynthesis and respiration falls along a line with a near zero slope. As that slope approaches 2, we have primarily calcification and dissolution as the dominant processes. And we can estimate the ratio of net ecosystem calcification to productivity from the slope of a linear regression of data. The middle set of graphs show our salinity normalized total alkalinity and total carbon data for the dry and wet season. Again, this is our discrete data. And for high and low tide, we have a good linear fit, and we have NEC to NEP ratios of less than 1, indicating that we have strong biological influence from photosynthesis and respiration. But we're also getting some influence from calcification and dissolution, and particularly during the wet season and low tide when we have slightly higher NEC to NEP ratios. And these results provide some additional evidence that photosynthesis and carbonate dissolution may also help buffer pH and acidification in the bay. However, we have a very limited amount of discrete data, and most of that data is from daytime. And so next slide, please. As a next step, we're in the process of developing and testing empirical models using our discrete data for estimating total alkalinity and total carbon from our sensor data so that we can perform a more comprehensive analysis of the full carbonate system at the hourly resolution of our sensor measurements. And we're also beginning to examine the impact of algae blooms on acidification and the relative influence of seagrass and algae bloom photosynthesis in the bay. And also, we are currently analyzing our 2020 and 2021 sensor data and discrete data to expand our time series analyses. Next slide, please. Just a quick summary. We see that pH has increased in Tampa Bay as seagrass has been restored, which can help buffer acidification through photosynthesis. Our pilot studies show evidence for local benefit from seagrass photosynthesis and carbonate dissolution in seagrass beds. Our sensor data indicate exposure to low pH, high CO2 acidification conditions, primarily during the wet season. Photosynthesis, respiration, calcification, and dissolution are primary influences on bay carbonate chemistry, and particularly at our site. And our results provide further evidence that photosynthesis and carbonate dissolution help mitigate low pH conditions in Tampa Bay. And I might be out of time, but thank you, and I'll take questions if we have time.
So Kim, we are out of time, so we'll have to hold questions. For those tuning in online, you can put your questions in the chat, and at the end, we might be able to get to them. Bear with us as Ed's pulling up the next presentation from Chris Moore.
Okay, and while Ed's doing that, I will introduce Chris Moore. Chris will be presenting next on a survey of spatial and temporal carbonate system variations in 4 major rivers of Tampa Bay. Chris just completed his master's degree at USF and is now an oceanographer at the U.S. Geological Survey. And when you're ready, Chris, I will hand it over to you.
Okay, thank you, everyone. Thank you, Kim. Thank you, everyone, for attending my virtual presentation regarding a recent spatial and temporal survey of carbonate system or CO2 system parameters in 4 major rivers of Tampa Bay. As Kim mentioned, this work was performed with my advisor, Dr. Bob Byrne, and Kim as part of a larger study for my master's degree at the University of South Florida College of Marine Science. All right, next slide, please. So many of you are familiar with the principles of ocean acidification, where the ocean absorbs excess CO2 in the atmosphere, resulting in a decrease in pH, i.e. acidification, and also a decrease in the concentration of carbonate ions. In coastal and estuarine environments, this acidification process can be exacerbated due to natural and anthropogenic fluxes in the form of freshwater input, nutrients, and carbon. These fluxes are largely driven by riverine input, which makes these systems very challenging to study through space and time. Next slide, please. So rivers have a major influence on the CO2 system chemistry of Tampa Bay, and yet to date, only one river has really been studied regarding the freshwater fluxes and carbonate system parameters. That study was in 2007 by Pillsbury and Byrne, and they conducted a spatial and temporal survey on the Hillsborough River and measured pH, saturation state, carbonate alkalinity, and some other major ions, and essentially found that during periods of low precipitation or low rainfall, pH and carbonate alkalinity were elevated, and waters were supersaturated with respect to calcium carbonate. And conversely, during high precipitation or high rainfall, river water was low in pH and carbonate alkalinity, and waters were undersaturated with respect to calcium carbonate. Next slide, please. So for this study, I was motivated to use recent advancements in spectrophotometric methods and scale our understanding of the CO2 system of the freshwater inflow into the bay. Therefore, I conducted this survey of CO2 systems in 4 major rivers, the Hillsborough, the Alafaya, the Little Manatee, and the Manitou rivers, to first provide a baseline against future acidification. Second, to assess the relationship between the river's CO2 chemical conditions and their drainage basins. And third, to determine whether the river's CO2 systems influence the seasonal characteristics of the water masses that mix into the bay and exit to the Gulf of Mexico. So, over a period of 1 year in 2019, each of the 4 rivers listed here were sampled twice over 4 consecutive weekends, first during the dry season, second during the wet season. When sampling each river, a small boat was outfitted with a flow-through reservoir to sample surficial waters, sequentially starting in the bay, upriver to freshwater conditions, where hourly water samples were collected for 24 hours at a freshwater location on each river. Next slide, please. So here on the top left of the screen, you can see an example of a 20-foot skiff packed to the gills with scientific gear. And on the starboard side there in the black and yellow bin, you can see the flow-through reservoir that I mentioned that's shown in the graphic to the right of that photo. Within the reservoir, there was a temperature probe that was plumbed to a thermosalinograph that determined temperature and salinity continuously. And at each sampling event, water samples were collected from the reservoir, first for spectrophotometric pH analysis, which was performed on board. Second, water samples were collected for total dissolved inorganic carbon, which I'll be referring to here as CT, we collected water samples for total alkalinity, which I'll be referring to as AT, and we also collected water samples for calcium analysis for saturation state calculations. Lastly, water samples were also collected for major inorganic nutrients, but I won't be discussing those results today. Next slide, please. So CT and AT results, CT once again being dissolved inorganic carbon, showed distinct differences where dry season concentrations substantially exceeded wet season concentrations. This first figure here you see on the top left contains the 24-hour CT measurements from each river positioned north to south, beginning with the Hillsborough and the southernmost river being the Manatee, from left to right. The dark boxes indicate nighttime conditions during that 24-hour period. Seasonal CT ratios from the dry to wet season for each river range from 1.4 on the Alafia to 1.85 on the Manatee. Click, please. Here we go. This second figure to the right contains the AT results for each river, and like CT results, dry season concentrations exceeded wet season concentrations, and the seasonal ratios range from 1.48 on the Alafia to as high as 3.6 on the Manatee. Click one more time, please. Now, due to these higher dry season AT-CT ratios, pH, shown in this figure, was substantially elevated in the dry season. Average seasonal differences in pH ranged from 0.24 on the Alafia to as great as 0.72 on the Little Manatee River. Next slide, please. All right, this table contains 24-hour average CT, AT, and pH on each river for each season. Let's take a look and just notice the considerable range of concentrations observed on each river during each season. Please click one more time. This table highlights the ratio of AT to CT within those blue boxes. What I want to point out is in the dry season, you can see that ratios were broadly consistent between the four rivers, ranging from 0.85 to 0.9, while during the wet season, ratios were much more variable between the rivers, ranging from 0.5 to 0.89. Next slide, please. So as I mentioned, the ratio of AT to CT strongly affects pH and saturation state, mainly from photosynthesis and respiration when different water masses aren't mixing. Consistent with that expectation, this figure shows the robust relationship between pH and AT-CT ratios each season. Dry seasons on the left there in black, wet seasons in gray to the right. Note the pH range in the wet season is much larger than the dry season. And lastly, distinctions can be made regarding river buffer intensity. Please click. In this second figure, here buffer intensity is highlighted where the standard deviation of the 24-hour average pH for each river is shown as a function of each river's 24-hour average AT. You can see as the average standard deviation of pH increased, AT decreased for all four rivers. The same can be said for CT, which isn't shown here. The daily variability of the poorly buffered Manatee River is particularly notable each season, where you'll see in the dry and wet season, it's located on the upper left of each of those graphs. Okay, next slide, please. So although the observations I'm presenting to you here are only 24-hour snapshots of the chemical conditions on each river, it was interesting to find a significant relationship between CT and AT concentrations and river discharge rates. Here, CT and AT strongly correlate with river discharge on the free-flowing Alafia and Little Manatee rivers during the wet season. Dry season correlations were much weaker. This relationship is consistent with the seasonal decrease in CT and AT that we saw with increased river flow in the wet season. Next slide, please. So the magnitude of this seasonal relationship between river discharge and CT and AT is shown here, where the average CT and AT is compared to the average discharge rate each season. Here you can see a substantial decrease in both CT and AT concentrations with increasing river discharge for each river. So in addition to the influence of discharge, this figure also shows the difference between CT and AT is smaller in the dry season, shown by the spaces between the boxes and squares for each river, where the AT-CT ratios were larger, which is consistent with the elevated pH we observed in the dry season. Next slide, please. So this table here gives you a sense of the prevailing physical flow conditions and drainage area for each river compared to the 2019 average discharge rates I encountered during each season's sample collection on each river highlighted in blue. Please click. So as using these flow conditions to better understand the significance of riverine CO2 system inputs to Tampa Bay, it's useful to compare the average CT and AT input from the 4 rivers mixed during each season to the CT and AT measurements made at the USGS site at the Middle Bay that Kim showed in the last presentation. In the dry season, you can see that the flow-weighted river averages of CT and AT were similar to the Middle Bay CT and AT collected by the USGS. This implies there's a salinity gradient throughout the bay of near constant AT and CT in the bay. Now in the wet season, the flow-weighted river averages are about half of the dry season concentrations. Therefore, CT and AT input from the rivers in the wet season contributes to lowering the bay's average CT and AT concentrations. Click one more time for me. So as a means of conceptualizing the CO2 system inputs to the bay, it's useful to consider replacement times using these flow-weighted river averages of CT and AT and bay volumes. As such, replacement times for Tampa Bay are on the scale you could see of several years, while replacement times for Hillsborough Bay using inputs from only the Hillsborough and Alafaya rivers is on the scale of months. So it's clear the rivers exert a modest impact on CT and AT in Tampa Bay, but have a substantial impact on Hillsborough Bay in the wet season. Next slide, please. All right, this table gives you, well, here we go. Riverine discharge is ultimately controlled by precipitation, watershed size, and groundwater discharge. As such, this figure here shows that average annual discharge from each river is strongly related to watershed area. Now, notably in Florida, a larger watershed is likely to encompass a larger number of identified springs that contribute to groundwater discharge. Due to underlying geology in Tampa Bay, the Little Manatee and Manatee rivers have no known major springs, while the Hillsborough and Alafaya both contain several. This distinction suggests that springs significantly contribute to the observed discharge differences of these 4 rivers. Therefore, it's reasonable to presume the elevated CT and AT concentrations observed on the Hillsborough and Alafaya rivers is partly due to prolonged contact time with spring water and limestone within the aquifer. Click one more time for me. Thank you. All right, so here is calculated saturation state values using the measured calcium and calculated carbonate ion concentrations. And it highlights the influence of spring-fed rivers where calculated saturation state values were higher. Although no supersaturated conditions were observed, dry season values were significantly greater than wet season values, presumably due to that reduced contact time from considerable discharge increases in the wet season. Okay, next slide, please. Okay, so in summary, we found that CO2 system parameters were elevated in the dry season during low flow conditions compared to high flow conditions in the wet season. AT-CT ratios strongly controlled pH and followed those same seasonal flow patterns. Seasonal flow characteristics modestly impacted CT and AT in the bay when making those comparisons to the USGS Middle Bay site. And lastly, calcium carbonate saturation state responded to flow conditions where high flow conditions diluted those parameters used to calculate saturation state, which decreased calcium carbonate saturation state in the wet season. Okay, thank you very much. And if there's any time, I'll take any questions.
Thank you, Chris. And Maya says that we are out of time for questions, so please add questions to the chat for Chris to answer, or feel free to email him as well. Our next presentation is by Dr. Dennis Hanisak, and he's going to be presenting on monitoring coastal acidification in the Indian River Lagoon, Florida. Dennis is a research professor at the Harbor Branch Oceanographic Institute and Florida Atlantic University, and he's also the director of the Marine Ecosystem Health Program and director of education there. And Dennis, whenever you're ready, I will turn it over to you.
Kim, can you hear me?
I can hear you online. Maya or Ed, sound check in the room, please.
Great. So I want to thank everybody, Kim, for organizing the session, and Gary and his team for everything they've done. I've really enjoyed the meeting remotely on the other side of Florida, and I think giving us the opportunity to actually present our talks, speaking real time, is really nice. Much better than a lot of meetings where you just hit the play button and watch yourself like an old movie or something. I think this has been a very interesting session. You know, Nick set the stage really well, showing us the big picture of coastal acidification in our estuaries throughout the country, and then Kim, you know, focused in on coastal acidification in Tampa Bay and its relationship to the watershed. And then Chris just gave us a really nice look at the system of freshwater inflows into Tampa Bay. And in many ways, I think my task now is to kind of take us across the state a little bit, look at a little bit of a different estuary, and tell you what we've been doing very recently to incorporate a look at coastal acidification. So next slide. This is the Indian River Lagoon. It occupies 40% of Florida's east coast. It's directly across from Tampa Bay that you can see on the west coast. It's a shallow, long, skinny coastal estuary, well known for its biodiversity due to its overlap of more temperate biota to the north and more tropical biota to the south. Next slide. The Indian River Lagoon, I'll just say IRL, save some verbiage, has issues that are certainly not unique to estuaries throughout our country, throughout the world. And in particularly, you know, I've highlighted two that I didn't used to talk about hardly, but they've become much more significant, you know, in the last several years. And those are harmful algal blooms and climate change. And Florida now has plenty of HABs, unfortunately. The IRL is like, we have so many different types now. And it's ground zero for climate change, I think, in the continental United States. So next slide. I started the Indian River Lagoon Observatory about 11 years ago. And the initial idea was to basically just foster more collaboration, you know, more of us talking and sharing and disseminating our data, with the goal to better understand the Indian River Lagoon's ecological function and how to best manage the lagoon. Next slide. The signature program of ERLO has become the network of advanced observing stations that we call the Indian River Lagoon Observatory Network of Environmental Sensors, but that's a mouthful, so we just say ERLON. Next slide. This observation and prediction network is providing real-time, highly accurate, high-resolution biogeochemical and weather data, which I think is really important to also have weather data through a dedicated interactive website. And so you can see the long list of parameters, and it's an extensive list. And as I hinted, I think the meteorological data adds a lot of power to being able to understand what we see with changes in water quality. And then last year, as part of an initiative to upgrade ERLON's capabilities, we added additional sensors that I've highlighted here in red to upgrade our capabilities and have additional sensors that address specifically harmful algal blooms and coastal acidification. Next slide shows a map to the left. We started our first station in 2013, expanded to 10 stations in the IRL in the St. Lucie estuary by 2016. It is a pretty fast ramp up, and I suggest if you do this, take your time, because once you start, it never ends. We have 3 new sites that in the northern IRL, which are not shown on this map, that were installed earlier this year, and their data will be publicly available later this month. Next slide. We have a dedicated website that we took over. Initially, we relied on the vendor of the equipment, and we decided that we have a lot more opportunities to customize it and change visualizations and things like that. So we did this again about a little more than a year and a half ago. And you can look at any of our data, either currently or those that have been archived, and you can look at their relationships. Next slide. So anybody can do that. Anybody can load the data down. We have all kinds of people who use it, and they can do whatever they want with it. So it is publicly available, 20 minutes after the data are collected. And it's a tremendous amount of data, and it allows us to monitor environmental challenges in this unique estuary. It's also a lot of data for research and planning managers to make informed decisions, for modelers to use in their models. And lastly, I think very importantly, platforms like these are great for students and the public to learn about water quality in the lagoon. Next slide. So specifically to address coastal acidification, we did add PCO2 sensors, and basically we relied heavily on what Kim had talked about in the Tampa Bay. We actually looked at things that people were doing all throughout the world, and in the end we decided that was what we thought would work the best, and it was right across the state. And we have had some nice inputs from Kim and her group as to how to proceed. And this will allow us, of course, as previous speakers have shown, to calculate remaining carbonate system parameters, including aragonite saturation, which I think everyone knows is a real important component of the story. And next slide, we can probably just keep on very briefly because this has been covered really nicely, not only schematically, but with real data from the west coast of Florida. I'll add to what Nick said earlier. Ocean acidification is one thing, and coastal acidification is like just so much more, and it's just become a very interesting thing to study. Next slide. So I want to show some data. This is 3 months of our PCO2 data. So that was July through September of last year, and you can just see very quickly there are huge differences among our stations. This, I can't do this with my mouse, but if you just look at the stations that are near the bottom of the list there for CO2, those are our 3 sites nearest the inlets, and the ones that are most upstream, highest up, are most upstream in the St. Lucie Estuary, and that actually is the site where, when Lake Okeechobee discharges occur, which were not an issue during this one, that's where they occur. So you can see there's this huge gradient. Next slide. And if we just kind of focus in more on just that St. Lucie Estuary story, you can see a little insert there in the graph that can show you the different locations of the stations. And also you'll see that we actually took some of the data from the Tampa Bay station being monitored by Kim and her USGS team, and we kind of showed that at the bottom as a reference point for Middle Tampa Bay. And it was, I think one of the coolest things was when we looked at that and we said, wow, our site near our inlet is very similar to what happens in a site in Tampa Bay. And I think that shows the value of doing these kinds of monitoring efforts, as Nick said, so many different places throughout the country, but even more particularly in a state like Florida, where so much is going on in terms of these changes. And let's see, the differences between, as one goes upstream, basically we get lower salinity and we get elevated organic matter. You can see that with our CDOM data, elevated nitrogen, as in nitrate and phosphate, which we also monitor. And there is this huge difference in PCO2. If we look at the next slide, these are the means for our stations. And again, to the extreme right is the Tampa Bay station for these same 3 months. And so, just to show you how many data observations they're listed there, but in that brief period of time, we had between 1,500 and 2,100 hourly measurements. So that's a lot of data. And as you've seen from the other presentations, that data really adds great power to our observations. The lowest PCO2 concentration was around 568 parts per million, and that was at the station that is in the Inner Lagoon, very close to the St. Lucie Inlet, and that's the one that approximates the Tampa Bay site, as I mentioned earlier. And then you can see how quickly things ramp up upstream, and then in the order of 3,000 to 4,000 parts per million, and then ultimately up to 7,500 parts per million. If we take a look at the next slide, now this is just, let's look at one station. So this is like in the center of the stations that I just showed you. We call this the St. Lucie Estuary, mid-estuary. For those who know where Stewart is, this is right by the Roosevelt Bridge. So it's a heavily sampled area. It's a kind of a really key location. And this now is just taking a look at 3 months in the dry season, and you can see, not unlike what was shown earlier for Tampa Bay, that physical control is primarily driven by temperature, and you can see here the strong effects on temperature on PCO2. And salinity, next slide, is a secondary physical parameter, which I think also was consistent with what you heard earlier. Next slide shows you, again, kind of is like, yes, we see that too. Here is biological control on PCO2 is also evident. Here's the dissolved oxygen concentration and PCO2 levels during that same dry season. And next slide shows you the pattern for pH, which again, not surprisingly, also strongly influences, is related to PCO2. The drivers for the wet season are I think more complicated, especially in our system. And I think that we would like to spend more time teasing them out better this year to really look at all of the things that go into it. But they are heavily influenced by some of the other parameters that we are monitoring. So next slide. A lot of time people say, is it really worth it? Is it worth all the time and the money? And, the instrumentation is not cheap. It takes a lot of work, much more than most people realize, to keep one site going and to keep a whole network going. It's a challenge, but I think it is worth it. And I think these types of continuous monitoring data enable us to better understand and quantify relationships between environmental factors and various processes and estuaries. I think the technology is wonderful. It's challenging too, as I've hinted at, but enables all of us to identify and better understand long-term ecosystem changes that are driven by events such as freshwater discharges, drought storms, algal blooms, and coastal acidification. And next slide, in particular to coastal acidification, I think most of us now realize that all marine plants and animals will be impacted to some degree. Some we could consider winners, some could be considered losers. I think we also, everyone probably this meeting knows that coastal ecosystem services most impacted and greatest at risk are calcium carbonate producing organisms, which are a really big deal in our estuaries, and especially here, specifically in Florida and in the Lagoon. So some of our restorations, like for shellfish restoration, are vulnerable to coastal acidification. And I think that it's critical to better monitor coastal acidification in these waters to help inform policymakers, resource managers, and shellfish aquaculturists, for example. Next slide. And as already mentioned, and Kim had some really nice data to support this, but other restoration efforts can locally ameliorate the impacts of coastal acidification. I'm specifically thinking here in terms of any kind of nutrient reduction is going to be helpful, but also restoration of seagrass beds, which he had talked about how seagrasses can alter pH and so on. And this has become such an enormous hot topic this past year due to the manatee mortality event, aka starvation, that started last year and is continuing this year. So no doubt we'll increase our efforts to in the estuaries to co-locate shellfish and seagrass restoration efforts when possible. And I think to a large extent, additional monitoring like this can be extremely helpful to show long-term changes, but also just in terms of maybe which sites might be better to work. Next slide. So in summary, estuaries such as the IRL are being threatened by coastal acidification. Networks of environmental sensors such as ERLON that measure key coastal acidification parameters are necessary so that we can detect real trends in coastal acidification, guide management efforts, and guide mitigation strategies such as seagrass restoration. And my last slide, I believe, is to thank a lot of people. It takes a huge team of really good people to make this work. And I've had the absolute best people now that have ever been on the project. And we've also had great support from various sponsors that are listed here. And you can see some of the other sources of information on ERLON. I think my contact information is there. Certainly it's in the program. And you can always ping me. And I don't have any idea if there's time for questions because I can't see anything hardly on my computer right now.
Thank you, Dennis. We are actually out of time for questions, so please email Dennis or add it to the chat if you have any questions for him. And while we're queuing up the next presentation, I'd like to introduce Dr. Phil Gravinese. He's going to be presenting on the effects of reduced pH on stone crab reproductive success. And Phil is an assistant professor at Florida Southern College in the Department of Biological Sciences. And whenever you're ready, Phil, I will hand it to you.
Okay, thanks, Kim. Can you hear me okay?
I can hear you online. Quick check, and we can hear you in the room.
Okay, great. Well, thank you everyone for being here today. I'm really excited to present some of the work we've been doing on the Florida stone crab in association with what the effects of ocean acidification or reduced pH might be on their reproductive success. And you can go ahead and click to the next slide, please. So I grew up outside of Philadelphia, and we spent a lot of my summers down at the South Jersey Shore fishing and crabbing with my grandfather. And we did a lot of crabbing for blue crabs. And during my time, just as an adolescent, we saw this decline in what we were catching. And I think a lot of these early life experiences are what drives so many of us to the ocean, and why the use of our oceans and bays has this connection as a coastal resource that connects us to these types of careers. You can go ahead and click to the next slide. And this can be reflected in our fisheries. We have a huge fishery economy here in the United States. You can go ahead and click. There's a couple animations on this slide. And so our US fisheries provide almost 2 million jobs, 9.5 billion pounds of seafood, and a huge revenue to an economic resource. Go ahead and click to the next slide, please. And so if you look at where some of that revenue is being parsed out, most of it's to the finfish. But if you go ahead and click, that $5.5 billion, about 30% of it represents lobsters, crabs, and shrimps. And go ahead and click to the next slide. And that's what we see here in Florida. We see a huge celebration of our iconic seafood species. Go ahead and click. Thank you. And so we see festivals in local towns and cities all up and down the coast of Florida celebrating things like the spiny lobster or the Florida stone crab. And that provides a huge economic input to many of our local communities. Go ahead and click, please. So the stone crab, Menippi mercenaria, which you see here, is one of those iconic fisheries that we have here in Florida. Go ahead and advance, thank you. And it's a unique fishery because unlike the blue crab fishery where we collect the whole animal, we only collect the claws from the stone crab. They remove the claws, the animals are then released, and they provide an annual harvest of around $30 million a year to Florida's economy. Go ahead and advance. Thank you. So over the last several years, we've seen this in the news. Where have all the stone crabs gone? There's a shortage in Florida. So those were both in 2017. And if you go ahead and click one more time, another bleak season back in 2012. And so you can look at these press releases as indications that this is a trend that's been going on not for a little bit of time now. Go ahead and click again. And if we look at the annual stone crab commercial landing, so here's years on the x-axis versus the total claws, millions of pounds. And again, this is the only real measure we have of the fishery because we don't take the whole animal. We see this pattern. And if you go ahead and click one more time, you can see that this is a declining trend. We do get some years where you see a good harvest, but those years have been bookended by progressively worse and worse years. This trend represents about a 30% decrease in the harvest since going back to 1999, and about a loss of 1.2 million pounds of claws in the fishery, which obviously the supply and demand has an impact there with the price of the claws when the harvest is lower. You can go ahead and advance. Thank you. So this plot is from the last stock assessment done by Florida Fish and Wildlife, and this goes back to all the way back to the 60s. And what I really want to show you is if you go ahead and click, if you look at these years from 1996 on to 2009, this is a fishing mortality ratio calculated by the Florida Fish and Wildlife based on several different metrics that they measure. And whenever this ratio becomes greater than 1, that's an indication that the harvest is, or the population is likely overfished. And that's what we see here. We see that this fishery has been put on some stress since the early 2000s, and they are definitely experiencing some overfishing. Go ahead and advance. So other reasons for the declining catch. So yeah, as I mentioned, there's been a 100-fold increase in traps since the 60s. Now there is now a trap reduction program going on, and but fishing pressure has definitely contributed. Go ahead and advance, please. And I don't want you to think that it's not just fishing, or that it's just fishing pressure that's going on. There's other factors that could also be contributing to their success. So we've heard a lot today in this session about the different effects of acidification in coastal areas. So changes in land use and decline in certain habitats. Go ahead and click again, please. The blue line there represents the stone crab's range. They can range all the way up to the Carolinas. And so if you look at where Floridians like to settle, this is from the US Census Bureau, we see this exponential increase in the population in Florida. And if you look at where we settle, we predominantly flock to the coastline. And so as we've heard about in this session, we have more development, you get organic runoff, and you can get excess nutrients in certain systems. And some of these can exacerbate the effects of coastal acidification, and in some estimates by 3 times what we expect for the end of the century. Go ahead and click, please. So they can experience this rate of change faster than what we project by some of our climate models. So the effects of reduced pH as a single stressor on crustaceans has been documented in the literature. Go ahead and click. So some deep sea crabs show increases in juvenile mortality. They also see decreases in larval carapace size. We have some intertidal organisms that are exposed to more variable pH, but they still show a decrease in survival and a change in embryonic heart rate, which has some implications for their metabolic output. Go ahead and click again, please. Some spider crabs in the North Atlantic, they show longer development time, upwards of a month longer to develop. And then go ahead and click one more time. Thank you. And then we've even seen some commercial species, in this example, a shrimp species in Japan, showing almost a 50% decrease in body size. So we do see variable effects depending on location and latitude, habitat, but we do see effects on these crustaceans. Go ahead and advance. So we tried to put this to the test with one of our species here in Florida. So this Florida stone crab's life cycle is similar to other brachyurian crustacean species. And so the females and the males come together and mate. This is usually a winter occurrence. Go ahead and click. Thank you. And so mating happens after the molt and the female is protected by the male. She'll then fertilize her eggs, extrude them onto her abdomen, and an early egg mass is indicative of this bright orange color, which is mostly yolk present in the embryos, and she'll attach them to her abdomen, brood them for about 2 weeks before, go ahead and click, before she releases the larvae, and you can click one more time. Thank you. And the larvae will then be transported out of coastal areas offshore where the larvae can have more stable conditions for development and also avoid visual predators. Go ahead and advance the slide, please. This is supposed to be a video. I don't know if it's going to work in this format. Nope. Okay, you can go back. Well, what you would have seen, oh, there we go. It's working. Fantastic. So when the females are ready to release their eggs, they get up on their legs here, as try to elevate the abdomen off of the benthos as much as they can. They flex those pleopods to help rupture the embryos. And then this isn't a bad or pixelated video. It's what you see in the water column there that looks like little tiny pixels are just the newly released larvae. They'll release 300 to 500,000 larvae in a clutch, and less than 1% of them will survive. But if they do survive, 2 years later, they will end up on someone's dinner plate. They go through 5 larval development stages. So stage 1, Zoea 1 stage at the top left, down, that's about 1.5 millimeters in size, all the way up to stage 5, which is about 2 or 3 millimeters in size. And then eventually molt into megalopy, where they'll reinvade coastal habitats. Go ahead and click. So to test this, we looked at the effects of reduced pH on their embryonic development. So here's an experimental system where we're acidifying seawater in the lab. Go ahead and click. So we had a low pH treatment and a control pH treatment. That was around 8.0. Go ahead and click. So we looked at embryonic development over time. And so we sampled eggs every day during their embryonic development. Go ahead and advance. And over time, we can identify the different embryo stages of development, both by visual display of their egg masses and presence of different morphological features in the embryo. And so you can get an estimate of their development time. Go ahead and advance. To look at hatching success, we waited till the female was about 24 hours from hatching. We then removed a subsample of the embryos, kept them isolated in the same environmental conditions that we were exposing the female to. And then once the female hatched, we then went back to those embryos and looked at, go ahead and click. We looked at the ratio of hatched to unhatched eggs under a microscope to get an estimate of hatching success. So for embryonic development, we have days on the x-axis, and we have the different developmental stages on the y-axis. You can go ahead and click. And so in the control, go ahead and, yep, thank you. It took about 10 days to complete their embryonic development. And then when we compare that to the acidic treatment, go ahead and click. Thank you. It is about 24% lower, or maybe about 2.5 days longer to complete their embryonic development. Go ahead and advance. Thank you. When we looked at hatching success, we had the same treatments, control versus reduced pH, over the median hatching success on the y-axis. You can go ahead, thank you. And when we compared those in the control, we had about 80% survive, or 80% hatch. Go ahead and click. Thank you. And then in the reduced pH treatment, you can go ahead and click again. We had a significantly lower hatching success, about a 28% reduction observed in the low pH treatment. Go ahead and advance. So in this study, we saw the effects on embryonic development, that there were some, they were developing a little bit slower. We also saw that their hatching success was reduced in lower pH conditions. Go ahead and click it one more time. Oh, that should be 28%, not 38%. So broader implications for this, the embryos, go ahead and you can advance the slide again. If there's less larvae releasing from the female, this could be a potential bottleneck event in some habitats, some locations, possibly reducing their larval supply, and that could potentially have an impact on the future of the fishery a couple of years down the road. Go ahead and click. Thank you. So one of the things that we were really interested in for the next component of this work was looking at this variability. So although we saw lower hatching success, this ranged from 20 to about 80%, which means that we still had a lot of females that were releasing embryos just fine under low pH conditions. So we want to see, is this variability representative of maybe it being exposed to prior environmental history, that they get experience with that pH variability, and go ahead and click again. So to do that, we were looking at conditions in seagrass habitats versus bare sand, and go ahead and click one more time, please. And I'm going to leave it there because my student Morgan is going to talk next about what we saw in the work that we were doing over the last couple of summers in Tampa Bay. You can go ahead and advance one more time. So I'd like to thank a lot of different partners here. This work was done in collaboration with Moat Marine Lab for the Protected Reef Program, Florida Institute of Technology, Florida Fish and Wildlife, and also Tampa Bay Estuary Program, who funded the Tampa Bay work. Thank you.
Thank you, Phil. Maya, any time for questions?
Kim, you have time for one question, or you can defer any extra time to the end after the student's presentation.
Phil, if it's okay with you, we'll defer questions to the end.
Yes, that sounds. Yep, that sounds great. I'm okay with that.
Okay, great. Thank you.
Yep,
so
thank you.
Our final presentation will be by Morgan Jarrett. She's going to present on do pH variable habitats provide refuge for the Florida stone crab from ocean acidification? Morgan is currently a student at Florida Southern College working with Phil on ocean acidification. And Morgan, whenever you're ready, feel free to take it away.
Okay, can you hear me?
We can hear you online. And Maya, sound check in the room. Maya? Yes, we can hear you in the room. Thank you, Morgan.
Okay, perfect. Thank you. So yeah, my name is Morgan. I'm a senior at Florida Southern College in Lagoon, Florida. First, I want to give thanks to the Tampa Bay Environmental Restoration Fund for funding this project, and to Florida Southern College for granting me a student faculty collaborative research grant for my participation in this project. Next slide, please. Okay, so as we've heard throughout this whole session today, the Tampa Bay has a variability in their pH, and this is due to it being a coastal area, having higher CO2 concentrations than an offshore area. And this can be due to increased runoff or increased rates of acidification in these coastal habitats. And one thing that we were really interested in is looking at pH diurnal variability depending on their habitat. And this graph on the right side of the screen is from the Tampa Bay Lobo database, and it's just showing that variability that I'm talking about between morning and night in the Tampa Bay. Next slide, please. So the animal of interest in this study was the Florida stone crab, which, as Dr. Gravinese had mentioned, is an economically important fishery in the state of Florida. In the year 2015, it brought in about $30 million, and as he described, the claws are taken from these crabs and they're returned to the water to regenerate after a certain amount of time. And since the year 2000, we've seen negative trends in the landings that fishermen have caught, and also a carapace width. The carapace width has declined since the year 2000 as well. This has led to about a 40 to 100% mortality rate in the crabs due to this decline. And this has led researchers to believe that the fishery is possibly overexploiting the stock. Next slide, please. Next. One more. Okay, so this is that same graph that Dr. Gravinese had presented, just to give you another visual that since the year at least 1999, the total claws in millions of pounds have decreased, and that has continued to decrease up until now, the year 2022. Next slide. The purpose of this study was to determine if the habitats of varying pH can potentially provide refuge for the Florida stone crab against coastal acidification. And to do this, we looked at 3 different variables. We looked at the time it took crabs to hatch once they entered the lab, next, and hatching success of the crabs and the larval survival rate. Next slide. Next. And we'll pause there. So, a couple other field methods. One thing I do have to say is the study took place over 2 summers in 2021 It took place based out of Mote Marine Lab, and then in 2020 was based out of Mote Marine, and 2021 was based out of Florida Southern College, which is the research I participated in. So ovigerous female crabs were collected by hand by us and Dr. Gravinese with the help of Florida Fish and Wildlife. And we measured them and put them in traps in Fort DeSoto State Park. And we had two different traps. We had a sand, a seagrass site to test that diurnal variability. Next. So here is a little Google image of where our sites were. So this is Fort DeSoto State Park, and our seagrass was located about a mile away from our sand site. Next. And next. So at this site, we took water samples for chemistry analysis at dawn and dusk every day for the whole summer. And while we were doing that, we also checked the crabs that we had in our traps for egg masses. And if they had developed an egg mass, we would transport them back to our laboratory. And all of our seawater analysis was sent to USGS for them to send back to us. Next. So our lab component, when the crabs first entered the lab, they were assigned either control pH or reduced pH treatment. And then we took 50 larvae once they had hatched and placed them into a cup. And this cup was put into that tank that their mother had hatched them in. And to look at larval success, we would count them at 24, 48, 72, and 96 hours and see how many were alive, how many were dead. To measure hatching success, we used those pleopod hairs that Dr. Gravinese showed you a video of and counted the number of hatched, which was indicated by a translucent egg mass, or an unhatched, which had those larval stages in the top right corner of that screen. We also measured total alkalinity and pH, and our total alkalinity was calculated using the CO2 SIS program. Next. Okay, so these are some of our analyses from the lab. Our temperature, salinity, and total alkalinity were pretty much consistent across the board, but our pH was obviously different for reduced pH at 7.677, and these pH conditions were selected based off of future predictions of ocean acidification. Next slide, please. Next. Okay. So this is a graph of our field data, specifically our field pH. The sand site is located by the yellow line, and the seagrass is by the green. One thing I do want to note is there were more seagrass samples because in the summer of 2020, we had a miscommunication of where our traps were placed, and they all ended up being seagrass. So that sand data is just from the summer of 2021. But from this graph, I just wanted to kind of let you all look and see that diurnal variability we have in that seagrass site. Next. Okay, this is that graph that I had at the beginning of my presentation from Tampa Bay Lobo. You can hit next one more time. Just right there, yes. So this was just for the 2021 summer, but you can see a relatively consistent pH for most of the summer. Our lab had a pH of 7.9-ish, and the field site also had a pH of about 7.9. Next. So I did want to point out this little odd ball on the end of this graph here. This was the red tide event that took place in July of 2021 summer, right after that storm came through. Those of you in the Tampa Bay know what storm. So we actually had to end our research right before this event, or during this event. So this was kind of that halt to our project. Next. Next. And we can pause there. So this graph shows our days to hatch analysis. So when the crabs entered the lab, we counted how many days until they had hatched. Pretty self-explanatory there. So on the left is our sand field treatment, and then control and reduced pH is in black. And to the right is the seagrass. We can see that they are pretty consistent. There wasn't any significant difference between those treatments. And we're thinking this could potentially just be to the limited sample size we have in that sand field treatment. Next. Next. And pause there for a second. So this is our hatching success data analysis. So on that left is our sand site, and that shows that there's a trend of reduced hatching success, but this was not significant. As you can see, our sample size for sand was much smaller, especially in that OA treatment. And then on the right is the seagrass. And we also saw that there was no significant difference between those, even though we do have some variability. So there was no significant difference between the treatments, but there was a significant difference between the interactions. So if you can hit next twice. Yes, so we did see between the sand OA treatment and seagrass control treatment that there was a significant difference in success, along with sand OA and seagrass OA, with those seagrass OA crabs having more hatching success than others. And next. 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 Okay. So this is looking at stage 1 larval survival, and we only have stage 1 as of right now. We're still looking at the other stages, larval development, to see how they did survive, if there was any. But overall, this was recorded at 0 hours, 24, 48, 72, and 96 hours, like I had mentioned before. But what I want everybody to get from this graph is that we see a better larval survival in that seagrass reduced pH treatment than the sand. And next. Next. Okay. So a couple of the conclusions from this study that we are taking away. For time to hatch, we think that there's no difference due to the barriers that these these larvae face while in their mother's pleopod hairs. So they're facing barriers between blood, the fluid, until they reach the seawater. So this could just potentially be no impact on them. And in hatching success, it appears to benefit larvae in the seagrass site rather than the sand, which is interesting. It's rearing them for essentially the variability in the pH is rearing them for success in later stages of life. And then for larval survival, as of right now, our trend points that to a later larval survival being more sensitive to seawater conditions. Next and next. Yep, next. So overall, our take-home message is that these seagrass habitats are providing a refuge for stone crabs from ocean acidification. Next. And again, I just want to thank all these sponsors, USGS for our water and chemistry analysis, Florida Southern for providing our laboratory and funding, Estuary program for hosting us, and yeah. I don't think we have time for questions.
Thank you, Morgan. And I think we do have time for questions. And let's start with Morgan and Phil, since we skipped over Phil for questions. Maya, just clue me in or let us know if you see any hands.
Can you hear me?
Yes.
Okay, we do have time for questions. Did I see a hand over here? No. Help me out. All right. The OG.
Great job, guys. I appreciate the presentations. A question for you: what are your thoughts on the nature of the wet and dry deposition in terms of its chemistry and how it may be affecting coastal acidification?
Can you let us know who you're directing that question to, please?
Anyone who would like to weigh in?
This is Kim. I can certainly weigh in on that. If you're talking about wet and dry deposition with respect to the carbonate system, we clearly see lower pH during the wet season. This is primarily driven by the increased discharge from the rivers. We see lower total alkalinity and total carbon in that discharge during the wet season. And yet we're still able to maintain mean pHs in the bay of around 7.9, when during the wet season, we get pHs down as low as 6.7, I think it was, coming out of the river. And so this was one of the key clues for us that we actually have some very strong photosynthesis control and probably dissolution buffering a lot of the higher CO2 that we see coming into the bay during the wet season. And I think it's certainly significant that we see higher respiration as well in the bay during the warmer temperatures in the wet season. We get higher CO2s, but I think a lot of that is likely getting buffered by some pretty rapid dissolution. In some of our pilot studies, we saw a great deal of carbonate dissolution, and that's really effective at buffering those pHs. And we see a lot of that dissolution taking place during the wet season. Did I target the answer to your question appropriately? Is that what you were looking for?
I think so. Thank you. All right. Well, I'm going to move on to a couple of announcements before lunch, but I want to thank all of the panelists for the presentations this morning. It was an excellent and engaging morning, in my opinion.